So, hello everyone, and thank you for joining the talk today. My name is Wang, and I'm a PhD at Nanjing University in China. So, this is my great honor to present at the TrustML seminar. So, today I'm excited to share our recent work on heavy-tailed linear bandits, especially focused on Hoover regression with one-pass update. So, this work has just been published at the SML 2025. So here's the outline of my talk. So first, I will briefly review the setting of stochastic linear bandits, which is a classical sequential decision-making process, and then I will introduce the case when the reward distribution are half-tailed, and after that, I will present our main result and conclusion. So first, let me start with a quick review of the stochastic multi-arm bandits problem. So uh, multi-arm bandits problem, you can think this as a game with several slot machines or arms. So each time the player can pull one arm and receive a stochastic reward. So for example, here we choose three arms, and every time we can choose one arms and observe the corresponding reward. But each time we pull the same arm, we will observe different rewards. This is because the reward comes from a stochastic distribution. So the reward of i's arm are ID sampled from an unknown distribution with unknown means. And the main goal of the multi-arm bandit is actually to maximize the cumulative reward. So the key challenge here is that we don't know the distribution of each arm. So we need to like do the exploration to make sure we to know each distribution of each arm. And also we need to do the exploitation to make sure that we can get the maximize of the cumulative reward. So this is a trade-off of here. So this is because the sample number is like finite. We don't have infinite sample opportunity. So we need to balance the exploration and exploitation. So let's move from the multi-arm bandits to the stochastic linear bandits. So for the stochastic linear bandits, every arm is associated with a feature vector. So we think the arm has some side information. So at each round, the learner can choose an arm xt. So the xt here is a vector, a d-dimension vector. And then the environment will review a reward RT. And here we assume the linear reward model, which means the reward RT is equal to the inner product of arm xt and an unknown vector theta star with a noise eta. So here the theta star is actually some kind of things that presents the underlying preference of the environment, and the eta t is the stochastic noise. So the goal of the linear bandit is also to minimize the regrets, which is the gap between the cumulative reward of the best arm and our real received reward, cumulative reward. So this is the goal of the stochastic linear bandits. And the most classical algorithm for stochastic linear bandit is linear UCB. And the idea is quite simple. So the first thing is actually to estimate the unknown parameter theta star. And after we estimate theta star, we can do the arm selection based on the estimation. So for the estimation, since the reward model is actually a linear function, it's actually a linear regression problem. So we can directly use the least square, the regularized least square to estimate the theta. And after we have the estimation, we can use the UCB algorithm. So here we not directly choose the best arm we ever observed, but we have a bonus term. So here the first term here, the x transpose to theta hat means the exploitation. So it will encourage exploitation for better reward arm. And for the bonus term, the beta and the x norm here is actually represents the uncertainty of the arm selection. So the v here represents like the past data. So the v norm here means if this x has already been explored before. So this term is actually encourage exploration. So combine these two terms, this is the UCB algorithm, which can balancing the exploitation and exploration at the same time automatically. And this algorithm has already achieved a nice theoretical guarantee. That is, with high probability, the regret of linear UCB is at most like d times square t, where d is the dimension of the feature vector of each, and t is the time horizon. So the SLB or the stochastic linear bandits is actually a very powerful tools that can also be extended to other settings, like for the reinforcement learning, the linear MDP settings, where the reward and the transition matrix is all assumed to be linear, where the phi here is actually a feature vector, a feature mapping the state and the action into a unknown vector, and the theta and mu here is a unknown vector, unknown system vector. So here we can still apply the techniques from the linear UCB, which there's a very classical algorithm called LSVI UCB, which also use this square to estimate an unknown parameter, and then use the UCB structure to do the selection or to do the action selection. So this is SLB. So next, let's move to the heavy-tailed linear bandits. So far we have discussed stochastic linear bandits under the common assumption that is the noise eta is actually, we always assume that to be a sub-Gaussian noise, which means the randomness in the reward is relatively well-behaved and easy to control. But however, in many practical scenarios, this assumption is too strong. For example, in finance or online recommendation or other real-world system, the reward distribution can be much heavier than the sub-Gaussian case. So this motivates the study of the heavy-tailed linear bandits. So where we only assume that the 1 plus epsilon moment of the noise eta here is bounded. So notice that the sub-Gaussian means all moments is bounded, and bounded variance means that the two moments is bounded, which is corresponding to epsilon equal to 1. And here we consider epsilon is a number between 0 and 1, so this is a very heavy case. So this is the heavy-tailed noise. And the challenge here is that we cannot directly apply the previous used this square. This is because the quadratic loss function will give large penalty to the large deviation data. But here in the heavy-tailed noise case, the big deviation may be due to the heavy-tailed noise, since we observe the reward could be influenced by very outliers data. So here, the basic idea to reduce the impact of outliers there have three main ways. The first is to truncation, which means directly remove the data pair if the observed reward is so extreme. And another way is to do the median of means, which means instead of relying on single sample, we can repeat sampling a same arm for many times, and we take the median of the average as a more robust estimate of the mean. And the third is actually to choose the robust loss function. So before we use this square based on quadratic loss, and here we like to choose some other loss that has reduced the penalty for large deviation, but has enough penalty for normal data. So for the existing methods, they have some problems for the truncation and mid of means. So the analysis of truncation always relies on the assumption on the reward. Notice that before we focus on the heavy-tailed noise assumption based on the noise eta. So we assume the 1 plus epsilon moments of the eta is bounded. But here, truncation always relies on that the 1 plus epsilon moment of reward is bounded. So this cannot recover to noiseless case, because when the noise is zero, that the 1 plus epsilon moment of the noise will be zero. But here, the 1 plus epsilon moment of reward is still be a u, so it cannot split the case of noise case or the noiseless case. And the mean of means, as we just mentioned, it need to like repeat sample arm for many times, but not every case the arm set is fixed. So it's actually require the arm set to be fixed and have the ability to repeat that the arms can be repeat pooling, but it will not work in many scenarios, which we will mention later. So here we consider this motivates the use of a more robust loss function. So here we introduce a very classical loss function called Huber loss. So the Huber loss is different from the square loss. It will have the quadratic region here. So when the deviation of the data is small, which means we think it's a normal data, so we still give it the quadratic penalty. But if the deviation is so that we will give it a linear penalty. So this can this can downweight the inference and prevents the outliers from dominating the estimation. So this is the idea of Huber regression. So it has a very strict threshold here, tau, to make sure where is the quadratic region, where is the linear region. And based on the Huber laws, there is already a paper published at Europe's 2023 that achieves the very good result. So their paper proposed the heavy OFEL. So the heavy OFEL just replace the least square estimation to the adaptive Hooker regression in the what we just mentioned, linear UCB algorithm. So it used adaptive Hooker regression to do the parameter estimation and use the UCB to do arm selection. So here the L here is what we mentioned, the Huber loss, and the sigma and the tau is all used to control the threshold. And this algorithm already achieve a very elegant result that is the optimal for the heavy-tailed noise case, where the regret is bounded by d times t to 1 over 1 plus epsilon. So this is a very good, very nice works. But we found that this work has some problems, especially for the adaptive Hoover regression. That is actually need to at each run t, like we need to solve an optimization problem that depends on all past data here, and the computational cost is about t times log big T. So this is because for each data we need to compute gradient, which takes OT, and if we want to converge at each round, we need to about log big T gradient descent steps. So overall is T times log O big T. So meanwhile, the storage cost is also will go linearly with T since the time is growing. So we have to keep all past data in memory. So this is actually very impractical, especially here. The bandit setting is actually an online scenario, which we cannot afford that the cost goes linear with time. So for comparison, recall that in the stop Gaussian case, we use least square for the estimation, and least square has a very simple closed form solution that we can directly update its use the matrix VT and a vector ZT, and matrix VT and ZT can directly update with a one pass method, which is directly use the data at current rounds and the last round's VT minus one. So this means that we can directly use XT and RT for one just for one chance, and we can directly through the data. So this is very quick, and this motivates us that we should like design a one-pass algorithm for heavy-tailed linear bandits, which have not researched before. But some works has already designed one-pass algorithm based on MOM and truncation. But as we just mentioned, MOM and truncation requires some extra assumption, which is not very elegant. So we want to say if we can design a one-pass algorithm based on Huber regression. So next is our result. So our approach is based on the framework of armor mirror descent. So armor mirror descent is a very general and powerful framework in online learning. So at each time step, it updates the decision by minimizing in a linearized loss plus the regularization term, so which is measured by the Bregman divergence. So this structure makes it very extremely flexible, and many well-known online algorithms such as online gradient descent, online Newton step, and even H can be viewed as a special case of OMD. But note this that like in online learning setting, OMD is used as an algorithm for regret minimization. But here we're trying to use OMD for parameter estimation. So we propose the HVT UCB. So this algorithm is based on two key components. First is the OMD-based one-pass estimator. So here we can see we only use the current data, which is inside the LT, and the last round estimation to do the current round estimation. So this is actually a one-pass algorithm, which can be rewrite as this format, which is one step of gradient descent followed by a projection with respect to the VT norm. So this means that we need only to process each new data sample once without revisiting all the past data, which makes the estimator computationally efficient and get rid of the dependency on the T. And it's only like some D23 or D22 order of computational cost. And for the upper confidence bound, we have need to like since we propose a new estimator, we need to analyze the estimation error bound for this OMD-based estimator. So we here propose the estimation error bound. So we think the estimation error at at round t is bounded by beta t, where beta t is a bound that's associated with t to 1 minus epsilon over 2 times 1 plus epsilon. So this is the estimation error. And we can compare this with the previous heavy OFAL algorithm. So heavy OFAL based on MLE kind of or offline algorithm, offline estimator. And here we use OMD, like the online algorithm. So the directly difference is that the computational cost per run is for heavy OFAL is OT, but for us is O1. We just talk about the dependency in OT. And we can achieve the same estimation error order like is exactly the same with heavy OFAL, but the cost of online update is that we will have a larger constant here. And since we have the same estimation error and we do the regret analyze and we find that we can also achieve the optimal regret bound, which is d times t to 1 over 1 plus epsilon. And furthermore, when if the null, which is the moment bound of noise, is time varying and known, the HVT UCB can further achieve the instance dependence bound, which here, when the node t is small, the bound will be tighter. So this will also match the instant dependent results that was previously established in the heavy OFAL. And so we can summarize the main results and compare it to the previous result. As we mentioned, MON truncation has already achieved the optimal regret. Also can achieve with one pass update, but they requires other assumptions like MOM algorithm requires fixed set and repeat pooling, and truncation requires the reward is bounded, but not the noise is bounded. And for the heavy OFAL, it can achieve the best result and instance dependent bound, but the cost is so big. So our algorithm can achieve the optimal regret and the instance dependent regret at the same time, both with only O1 computational cost. So this is our main result. So we can actually achieve the statistical efficiency and the computational efficiency at the same time. So let me briefly explain our estimation error analysis. So we can decompose the estimation error into three terms: the generalization gap and the stability term and the lagging term. So the generalization gap captures the effect of the noise. So here we actually compare the gradient of the noise loss with the noisy loss. So and the stability term comes from the online update, which means the cost of the OMD. So before we want to use OMD to mimic the full batch updates or MLE. So the negative term is actually a byproduct of the OMD framework and it actually helps us in the analyze. So the key step here is actually we want to design the parameter sigma and tau to make sure that after denoising, the data should stay in the quadratic region since it's actually a normal data. So this is an intuitive method. And to do this, we design a recursive normalization factor, which means the current round sigma, normalization sigma, is based on the last round estimation error. So this design, however, is actually introduced a major analysis challenge. So beta t here, so we design sigma t here is to bound the beta t here. So this means the beta t in the current round depends on the beta t minus 1 of the last round. But notice that each beta or the estimation error is actually holds with only high probability. So if we simply stack them together, that is a risk that overall the high probability guarantee will be failed. So to resolve this, we developed a very careful inductive proof, which shows that the recursive design is still valid and the high probability guarantee remains across all the rounds. And for the stability analyze, it actually shows the challenge of using one pass OMD to approximate the full batch MLE. So we can split it into two parts. The first is the stochastic part, which can be handled by standard concentration techniques, and the second is deterministic part, which is more tricky. So in previous analysis of OMD, the deterministic part it could be bounded like use a potential lemma, especially it shows that the term before the norm is actually without the sigma is actually a bounded term. And so the sum of the x norm can be dealt with by the potential lemma. But here notice that since we are in the habitable noise case, so here we have a normalizing factor sigma here, and the sigma could be very small, which means this term could be unbounded. So so we found that this actually the term here is actually the same structure with the negative term. So we're trying to bound the norm here to make sure this term can be cancelled with the negative term. And for the generalization gap, this actually shows the challenge of handling Hoover loss and the habitated noise. So we can split it into two parts. One is the challenge brought by the special structure of Hoover loss, and we can also control this by some concentration techniques. And for the habitated noise, since we already controlled it by the Hoover loss, by the the normalization and some threshold, it can be controlled by the self-normalized concentration. And next is the experimental results. So we evaluate our algorithm on the various scenarios, including different habitable noise, like student T, Pareto, and we're trying to show our ability on the dynamic onset and time varying the bounded norm. And we show that we can also we can get the similar performance comparable to the heavy OFL, which is the offline estimator. And our time cost is very efficient compared to the heavy OFL. And actually, our method can have some two potential extensions. So for the first is the online linear MTP. So notice that in the linear MTP, the reward, the realizable reward is can be shown at like this format. The phi here is a feature mapping that map the state and action into a known vector, and the theta here is the unknown vector, and the epsilon here is the habitable noise. So the problem is that we need to estimate the rewards in the linear MDP. And as we mentioned, in this case, the MOM algorithm will fail. This is because the MOM need to repeat sampling. But here, after we choose an action, the state will transit, which means we cannot choose a same feature vector. So the MOM algorithm will fail under the linear MTP setting. And our algorithm, we don't rely on other assumptions. So maybe our algorithm can be directly applied on the linear MTP setting. And another one is the adaptive control. So the adaptive control consider the state transition system where X here is the state and the U here is the control, and A and B are unknown states, unknown system matrix. W here is the habitable noise. So here we still need to deal with like the habitable noise or the boundary variance noise. So it's just same as the linear MDP, the MOM will fail because the state will transit. So like use OMD, use our Hoover regression based OMD algorithm can be like directly applied on this kind of scenario. So besides, we also need to emphasize that before our work on habitable linear bandits, the one-pass concern has already been appeared in the study of generalized linear bandits. So the generalized linear bandits is a more general case of linear bandits where the reward is not a linear function, but with the extra link function mu here. So for example, the logistic bandits, the mu here is the sigmoid function. And the problem is that for the MLE, for the GLB setting, we cannot directly use the least square since the loss is nonlinear. The reward is nonlinear, so we need to use the maximum likelihood estimation, MLE. So it does not have the closed form solution, which meets the same challenge as the habitable linear bandits. So the first algorithm for GLB can achieve the kappa times square t regret, where kappa is the nonlinearity, which measures the nonlinearity, and the cost per round is OT. So this is the exactly same situation with our habitable case. And so in 2016, our algorithm was proposed called OL2M. So this is the first one-pass algorithm for a special case of GLB called logistic bandits. So it uses online neural step to estimate the parameter, and it can still achieve the kappa times square t regret, but can directly improve the computational cost to 0.1. But notice that the kappa times square t is not the optimal regret, since the kappa here can be extremely large. exponentially increasing. So the first works considered like using the implicit OMD to do the parameter estimation. But so this can achieve the statistical efficiency, the optimal regrets, but it has a larger computational cost per round for log big T. So this is because it's actually optimizing over the original loss function, L here. So which means at each round, it will do like log T round gradient descent step for convergence. So the computational cost is not efficient enough. So and finally, a recent work like by Jiang and Sugiyama at 2026, 2027, 2023 proposed a joint efficient optimistic algorithm called OFU M log B. So this algorithm do two things. First is it's not directly optimize the original loss function, but use a second order approximation. So this can ensure the computational efficiency. And second is still use liquid head and Hessian approximation for the statistical efficiency. So the algorithm can achieve the optimal regret with per round cost of 1. So it's a joint statistical and computational efficient algorithm. And the algorithm can also be extended to multinomial logistic bandits where the feedback is not binary but multiple feedback, like to 0 to k. And also achieve like a statistical and computational efficient result. And besides, these techniques can also be applied to like RLHF, since RLHF is also like a binary feedback, and we need to like estimate the unknown parameter in the BT model for the preference. So it's a setting similar to logistic bandits, but not exactly the same, since it's actually corresponding to another setting called dueling bandits, where at each round a learner can choose two XT and YT, and the environment reveals the preference feedback OT. So we always use the BT model to model this preference function. And this requires us to estimate the unknown parameter. So here, so it can share the same techniques from the just now we mentioned logistic bandits, use the second order approximation and look at norm and to do the parameter estimation. So, but notice that although we all use OMD for estimation, the difficulty is totally different. Like for logistic bandits, they use OMD, and difficulty is for how to deal with the nonlinearity, part kappa. And for Habitat case, we also use OMD, but our challenge is that how to set the threshold or the normalizing factor to make sure that the normal data is stayed in the quadratic region and the outliers are staying in the linear region. So this is actually totally different difficulties and cannot direct apply their techniques into our settings. So finally is the conclusion. So we consider the Habitat linear bandits where the only one plus epsilon moment of the noise is finite, with epsilon is a number in size 0 to 1. And our approach is Hoover loss-based one-pass algorithm, where we employing OMD with tiered local norm to replace the MLE in SLB in stochastic linear bandits. So we can achieve the optimal and instance-dependent regret bound with only O1 cost, where we only consider the dependency on T. And there's also some open questions about like how to handle unknown variance nullity while maintaining current guarantee. Some kind of works already solve this in RL settings, but we don't know if we can solve this in the Habitat noise case. And this is a joint work with Yujie Zhang from RIKEN AIP and Professor Peng Zhao from Nanjing University and Professor Zhuhua Zhou from Nanjing University, and has been just published at ICML 2025. Thank you very much for your attention. Yes. So is there any question?
Thanks for the great talk. So is there any questions? You can just speak up. Yeah.
Hello.
Hello.
Hi. I have a question related to the covariates. So I wondered if I understand correctly, the current assumption on the covariate is that it's got to be constrained within a ball. Is it possible to adapt this framework to a situation where you have contextual stochastic bandits but the covariate is not constrained to a ball. It can be sort of the covariate as well can potentially be heavy-tailed.
Oh, I'm sorry. So what's the covariant you mentioned here? Is the
the feature vector.
the feature vector. Oh, okay. Yeah,
Right.
yes, right. So yes, the feature vector here, like for the x, is actually is bounded by a ball, right? Exactly. So and can you repeat your question again?
So I guess one application of this would be to like stochastic contextual bandits. And I wondered if you could, if there's maybe a potential to consider if this could be potentially integrated with a setting where the contexts in a stochastic contextual bandit framework where both the noise and the contexts are heavy-tailed.
Yeah. So why I don't understand. So why the context should be heavy-tailed? It's actually a very deterministic term, right? We can observe all the context, and we just choose one. And yes,
Yeah, right. So in this framework, I guess, so here I'm sort of thinking more in a framework where you have an additional context vector zt. So let's say you have an action, we call our action xt, and then you have an additional context vector context zt, and your reward is determined by a combination of action and context. It could be potentially that you have.
I understand. So you mean the theta star here could be heavy-tailed or random vector here, the theta star here, right?
Yeah, I think I think it doesn't exactly correspond to theta star being heavy-tailed. It would correspond to I mean, I think essentially it corresponds to a framework where you have a I think if we want to import the so I think this framework can be used to understand the linear contextual bandit as well. And then I think in that case we would view it as like a changing action set.
Right. Oh, I
But then
understand.
I'm sort of
yeah, right. So that is actually yes, it's a different scenario that we can receive random context, and each arm doesn't have any other side information. So we need to to choose the action based on the general context. Yes, that's a great question. Yes. uh, yes, I never haven't considered that problem before. So yeah, yes, that's a great question. So I will consider it deeply. Yes, thank you.
Okay, maybe I have a more general question. So is there any maybe other robust laws that with the property similar to the Hilbert laws that can achieve such also some comparable results in your setting?
Yeah, great question. So there's another famous loss function called Catoni, so which is also a robust function, but it's actually it's also very famous. And there's also work like published in SML 2025, which is for the Catoni estimator, for linear bandits. So the main difference is that I think the Hilbert loss is more easier for analyze since it has a very simple structure, a direct quadratic function in one region with a threshold and a linear function. So this is actually very easier for estimation, for analyze. But the Catoni is actually a smooth version of Hilbert, which does not have this strict change point. So it's actually it's a very elegant loss function, but it's actually I think it's hard to analyze in this case, and it's actually hard to switch it into a one-pass algorithm. Yes.
Oh, okay, I see. I will looking for those reference papers. Okay, thank you for answering.
Thank you.
So is there any questions?
Oh, hi. Hello. Actually, I'm wondering, I think the method can also apply to the time varying arm set.
Yes.
So
Actually,
even
right.
adversary arm set is also acceptable, I think.
Yes. Since we do not rely on the assumption that the arm set is fixed, actually we can directly apply that into like the max is inside the sum. It is exactly it directly change. Any need to change is like when doing the when doing the arm selection, the argmax here should be based on the time-varying arm set. Yes, this is the only change.
Yeah, thank you.
Okay, if there are no more other questions, then we will just finish here. And if you have any more questions, you can just contact Jiang Wang for any of other further discussions. Okay, thank you for attending. Yes, let's just finish here. Okay. Yeah, I will also attach the page, maybe the contacting information in the chat room. So yeah, if you have any further questions, you can just contact Jiang Wang through email or other communication tools. Yeah, thank you for attending.
Thank you everybody.